Welcome back to another Gungahlin College Maths Applications video lecture. The topic of the lecture today is going to be inverse matrices. So far with the topic of matrices, we've done matrix addition, matrix subtraction, and matrix multiplication. So you might think the next logical step would be to do matrix division. Unfortunately, there's not really something that we call matrix division, but there is something that's very close to that, which is what we're going to do today. So to start this off, I'd like to draw an analogy. So in normal math that you guys are used to doing, if you have the number a, so this is just a number, not a matrix, right? The number a, and you divide it by itself, you get the number 1, right? Hopefully we can all agree about that. So a divided by a is 1. But instead of doing that, we can also multiply by 1 over a, and also get 1. And in fact, this is doing exactly the same thing for just numbers. So a times 1 over a is also equal to 1. So what we actually say is that this guy here, this 1 over a, it undoes multiplying by a, so we're going to call it the multiplicative inverse of a. So I know it's a long name, but all it means is multiplicative means it multiplies, right? And inverse means it undoes multiplying by a. So since we don't have matrix division, we do actually have the multiplicative inverses of matrices. So if I have a matrix A, what I'd really like to do is find what the multiplicative inverse of A is. So the inverse matrix of A. So the inverse matrix of A we call A to the minus 1. So what properties should the inverse of A have? So just like this one over here, A times 1 over A, we should have, when we have the matrix A, when we multiply by its inverse, well, it can't be equal to 1, right? Because it's two matrices. We should expect it, though, for this to be equal to the identity matrix. Well, why is that? That's basically because the closest thing that we have for matrices to the number 1 is the identity matrix, and that's because if you multiply any matrix by the identity matrix, it gives you back that same matrix again, just like when you have a number and you multiply any number by 1, it gives you back the same number again. So not only this, A times A inverse equals the identity matrix, you'd also like, because remember, matrices don't commute, you'd like to be able to do this the other way around. A inverse times A should also be equal to the identity matrix. Alright, so what we're going to do now is I'm just going to tell you what the inverse of a 2 by 2 matrix is. So in this course, all you're going to have to do is be able to calculate the inverse of a 2 by 2 matrix. You're not going to have to worry about anything bigger like a 3 by 3 or a 4 by 4 matrix or anything messy like that. So the inverse of a 2 by 2 matrix. This is really the most important thing we're probably going to do today, is this bit right here. Tell you what the inverse of a 2 by 2 matrix is. So let's say we have a 2 by 2 matrix A. A is going to be A, B, C, D. Now the reason I'm keeping it like this and using symbols instead of numbers is because what we really want to do is come up with an equation that tells us what the inverse of any 2 by 2 matrix is. So I don't want to put it in numbers yet. We'll do examples later. So if we have this matrix A equals A, B, C, D, the inverse of A is equal to 1 divided by A times D minus B times C. So remember, these things here are just numbers. So this thing out here is just a number. 1 over AD times minus BC times the matrix, right? D, negative B, negative C, A. Okay, so it might seem a little bit confusing at first, but all we've really done, if we switch D and A around, right? When we had A here, it became D. When we had D, it became A. And B became negative B, and C became negative C. Okay, so that's the inverse of our matrix. Now one more thing is this number at the front here is really important. In fact, this thing on the bottom of the fraction, AD minus BC, has a special name. It's called the determinant. And it's so special that it actually has two different ways that we normally denote it. So sometimes we say det of A, and sometimes we write it like this. So A with two bars like that. So this is AD minus BC. Okay, so that's the inverse of a 2 by 2 matrix. So like I say, this is really the most important thing we're going to do today. So what I'm going to do is put it in a big red box so you don't forget that that's the most important part. Okay, so the next thing we're going to do is work out an example. So what I'd like you to do now when you're watching this video is, if you feel like you really understood this and can do it, I'm just going to write out an example, and I'd like you to pause the video and try to do it, and then you can actually fast forward and see whether or not you got it right. So I want to do the example where A is equal to 4, 5, 2, 3. So all I'm going to do is find the inverse of what this matrix is. So what that means is all I'm going to do is apply this formula up here, A inverse equals this stuff, to this particular example. So just to make this really clear, if I set this matrix A equal to this matrix here, A, B, C, D, we could say that little a was 4, little b was 5, little c was 2, and little d was 3. Okay. So now I can actually plug these numbers directly into this equation up here and work out what the inverse of A is. Okay, so A inverse is 1 over the determinant, so 1 over A times D, which is 4 times 3, minus B times C, which is 5 times 2. 1 over 4 times 3 minus 5 times 2 times the matrix. And remember I said we're going to switch these two numbers around, so 3 and 4. 5 becomes negative 5. 2 becomes negative 2. So let's simplify this number at the front. So that's 12 minus 10. So 1 over 12 minus 10 is 1/2 times 3, negative 5, negative 2, 4. Okay. So I can actually write this even more simply by multiplying the scalar by the matrix. So this becomes 3 divided by 2, negative 5 divided by 2, negative 2 divided by 2 is negative 1, and 4 divided by 2 is 2. Okay, so now what I want to do is actually show you that this equation for finding the inverse of a matrix actually gives you what we said we wanted the inverse of a matrix to be up here. So what I'm going to do is first of all multiply A by A inverse and find out whether or not it actually equals to the identity like we hope it does. So let's work this out. So A was 4, 5, 2, 3. And we're going to multiply that by this inverse. Now I'm actually going to use this one here with a 1/2 out the front, and that's because I figure you guys don't really like multiplying numbers by fractions a lot. So let's keep the fraction at the front for now. So I'm going to pull that out the front, and the reason I can write it out here is because it's a scalar, not a matrix, right? So we can actually change the order. So 4, 5, 2, 3, and then the inverse was 1/2 times 3, negative 5, negative 2, 4. Alright, so let's do this multiplication. So this is 1/2. I'm going to do this quickly because I figure you guys should be really good at matrix multiplication by now. So 4 times 3, so we're going to do row 1 times column 1, right? 4 times 3 is 12, plus 5 times negative 2 is negative 10, so 12 minus 10 is 2. Row 1, column 2 is row 1 times column 2, so 4 times negative 5 is negative 20, plus 5 times 4 is positive 20, negative 20 plus positive 20 is 0. Row 2, column 1, 2 times 3 is 6, plus 3 times negative 2 is negative 6, 6 minus 6 is 0. Row 2, column 2 is 2 times negative 5 is negative 10, plus 3 times 12 is 10, negative 10 plus 12 is 2. Alright, so now we can multiply by the scalar, and this gives us exactly like we'd hoped. 2 times 1/2 is 1, 0 times 1/2 is 0, 0 times 1/2 is 0, and 2 times 1/2 is 1. Now remember, this is a special matrix. It's called the identity matrix. So A times A inverse is actually the identity matrix. So now let's just do it the other way around, because remember, like we say, matrices don't commute. So whenever we do this, we have to double check that it works both ways around. So let's multiply A inverse times A. So A inverse was 1/2 times 3, negative 5, negative 2, 4, times A was 4, 5, 2, 3. Okay, so this is 1/2. 3 times 4 is 12, plus negative 5 times 2 is negative 10. 12 minus 10 is 2. Row 1 times column 2 is 3 times 5 is 15, plus negative 5 times 3 is negative 15. 15 minus 15 is 0. Row 2 times column 1, negative 2 times 4 is negative 8, plus 4 times 2 is 8. Negative 8 plus 8 is 0. Row 2 times column 2, negative 2 times 5 is negative 10. Negative 10 plus 4 times 3 is 12. Negative 10 plus 12 is 2. So we've actually shown that it doesn't matter which way you do it, both equal the identity. Okay, so that's our example. So let's do one more really quick example. So I'm going to call this one B. And I want the matrix B to be equal to 2, 4, 3, 6. And I want to calculate what B inverse is. Okay, so let's apply the formula to this. So remember, B inverse should be 1 over the determinant. The determinant was A times D, which is 2 times 6 is 12, minus B times C. B times C is 4 times 3, so 12. All right, so already you can see there's something funny here. 2, 4, 3, 6. Okay, so this determinant is actually 0. So this gives us 1 divided by 0 times this matrix, 2, 4, 3, 6. Now this to me looks like a problem, because we don't actually know how to divide 1 by 0, right? We don't need this. This is what we call undefined, right? 1 divided by 0 is infinite. So that's a bit of a problem, because our matrix, our inverse matrix, doesn't seem to exist, right? So what we actually say, so our determinant, right? A determinant is the bottom of this fraction. The determinant of B was 0. And when this happens, B inverse doesn't exist. Right? We can't find the inverse of the matrix. This is a special kind of example, and there are lots of these matrices where the determinant is 0 and the inverse doesn't exist. These guys are called B is a singular matrix. And all it means is that exactly like we can't divide a number by 0, we also can't find the inverse of a matrix where the determinant is 0. Okay, so that's all for this lecture. In the next lecture, what we're going to do is actually apply some of what we've been doing and solve some matrix equations. But that's all for now.